Hello, everyone. Welcome. This is Module 3 in our epidemiology session where we're going to talk about bias in epidemiologic studies. So our first part is going to be overview and talking about directed acyclic graphs. So this is our overview for Module 3 where we'll discuss about DAGs. We'll talk about confounding and finally talk about the two types of common bias that we see in epidemiologic study, particularly in cohort and case control study, including selection bias and information bias. Let's start with the overview and with DAGs. So our objective for the first part is to understand the difference between association and causation. This is something that we've talked about in the first part. Learn a little bit about internal and external validity, or what we call generalizability in epidemiologic studies. And we'll also talk about the different types of errors that we have in epidemiologic studies and how we can use the directed acyclic graphs or DAGs to represent causal structures. So like everything be it in epidemiology, like any relationship is complicated. It could be bidirectional or unidirectional. And any relationship doesn't imply causation. So let's start with the definition of association. So if we look at the English language Oxford Dictionary definition of association, it means the way in which two or more people or things are connected with each other. A thing's effect on or relevance to one another. So we could have a bidirectional relationship. So you have one thing bidirectional way, one affecting the other. The second one is we can see a unidirectional arrow, one affecting the other. This could be causal. So if we change one thing, the other thing may be changing or may not change. So if we look at causation, what we're saying is there is a cause and an effect. So causation means that there is an exposure that affects or that produces the effect. So we have the cause, and we have the effect. And you can see that it is a one-directional arrow. So if we remove the cause, the effect disappears. That's what we mean by causation. And we'll discuss this in a greater detail in the subsequent slides. So this is a classic example, quite simplistic, that we use in epidemiology, trying to distinguish between association and causation. So why is it important to distinguish between an association and a causation? Let's take this hypothetical example that a dry, hot, and sunny summer weather might cause individuals to crave for an ice cream, or there is an increased ice cream consumption, and also which might increase sunburn in some individuals. So we can say that exposure to sun is causing a sunburn, and exposure to sun is causing an increased consumption to an ice cream. But if one looks at the association between an ice cream consumption and a sunburn, they might find a strong association. But this is not a causation, this is a correlation. So as an epidemiologist, you want to identify the true causes of a disease by intervening in which we can control the disease. So when considering a relationship between an exposure and a health outcome, it is really important to distinguish between a relationship, a correlation, versus a causation. So in epidemiology, we ultimately want to be able to draw conclusion about causal association, but we might find correlations which are not necessarily causal, because both ice cream consumption and sunburn have a common cause. The two could be related to each other, even though there is no biological connection between the two. So as mentioned earlier in our study design, most epidemiologic studies are observational studies, and hence we observe association and we infer causation. And we move cautiously in inferring causality. And this is often done after we have sufficient studies in diverse settings. And this is a criteria that was developed by Bradford Hill more than 50 years ago, where he came up with the criteria for moving from association to causation. And those are important criteria that we try to take into account. So is there temporality? Does the cause precede the effect? So do you have the exposure prior to the outcome? Is the association consistent with existing knowledge? Biologically, what you're observing, does that make sense? Sometimes what you're observing may not necessarily make sense biologically. So you need biological plausibility as a second criteria. The third one is consistency. So anyone who looks at the association between smoking and lung cancer, we never had a randomized controlled trial to establish causality, but it is the totality, the consistency of studies across different settings that led us to infer causality. So have similar results been shown in other studies? You don't necessarily expect in all, but that is what you would expect in order to infer causality. The fourth one is, what is the strength of the association between the cause and the effect? So the presence of an association alone may not necessarily indicate causation, because there may be other sources that lead to an increased effect of the outcome. So we need to see the strengths of the association. The stronger the association, the more likely that the association is causal. The next one is a dose-response relationship. Does increasing the exposure increase the effect? So if you take the example of smoking, as the number of cigarettes smoked increases, the risk of lung cancer increases, indicating that there is a dose-response relationship, which implies that the association is probably causal. And then we have other criteria as well, including reversibility, which is, does removal of a cause decrease the risk of the effect? So if you remove the exposure, do you see attenuation of the effect or even a protective effect? Next one is study design. This is something that we've talked in study designs. So the evidence has to be based on a robust epidemiologic design. And finally is the evidence. How many lines of evidence lead to the conclusion? So this is a guideline that we typically use in epidemiology to infer causality from association studies. So what do we mean by a valid study? So if we take the literal definition, study validity is the degree to which the inference drawn from a study is warranted when you take into account the study methods. So this is an important word. So as I mentioned, many of our epidemiologic studies are observational studies. So we're trying to infer causation based on the body of evidence that we see. And we have to take into account some of the study methods. The fact that we're conducting observational studies indicates that there are some limitations or there are some methodologies involved in undertaking the study, and we have to take those into account. In other words, when we say study validity, we're saying, do the results reflect the truths after considering the strengths and the weaknesses of the study design and the methods? And we'll discuss some of the ways that a bias or a limitation or a weakness in a study method could compromise the quality of the study and undermine the study validity. So one of the ways that we define validity is classifying into two: an internal validity and an external validity. The first one, internal validity, it's often affected by study error. So we are asking the question, is the observed association between the exposure and the outcome reflect a true causal effect of the exposure under investigation? Are we estimating what we want to estimate? Are we measuring what we are implying to measure? This is something that we'll also discuss when we talk about instrument validation, when we discuss about construct validity. So are we really measuring what we are intending to measure? This can be affected, as I mentioned, by study errors. And oftentimes, this is something that could be anticipated, and there are some safeguards that one can put in place prior to designing a study. An external validity is the validity of applying conclusions of a scientific study outside the context of that study. So we've talked about, for example, a target population when we talked about discussing a study sample, study population, and a target population. So this is about generalizability. Oftentimes, you might hear the word external validity and generalizability used interchangeably. So can the results be extrapolated beyond the target population? There are some important considerations when one makes external validity or evaluates external validity. The first one is the study errors. Sometimes the internal validity can affect the external validity. If you're not really measuring what you think you're measuring, for example, if you're trying to assess psychosis, but you're not using the appropriate tool, and you're not measuring the different aspects of psychosis, then the internal validity will compromise your ability to generalize your study findings. So the two are related with each other. The second one is characteristics of the study sample compared with the target population or external population might be different. So this could affect generalizability. For example, if you take a specialty hospital or patients coming to a specific hospital for a specific reason, you compare that with the general population, that may not be appropriate. So looking at the characteristics of the study sample as well as the internal validity will be important for external validity. As I mentioned, the purpose of most of epidemiologic studies is to accurately measure the occurrence of diseases, the risk factors, and the association between the exposure and the outcome. Those were the purpose of the epidemiologic study. For any of those goals, there are many possibilities that study errors might happen, and so much attention has to be devoted for understanding the sources of error and for minimizing them. So epidemiologic studies can provide or inform public health policy and practice if the errors are taken into account. So we try to minimize those errors. However, no study is completely free of error, but errors could be minimized at the design stage, and we'll discuss those in the subsequent slides. So those errors, we oftentimes classify them into two types of errors. The first one is a random error, and the second one is a systematic error, what we often call bias. So a random error are essentially due to the fact that they can occur only if a study sample of a population, if the results from the study sample, we make an inference to the whole population. Depending on the population sample we take and depending on the time of the testing, the results of the testing will differ from simple random variation. So there could be a simple random variation that is introduced in your study. This may not be something that you can anticipate. This may not be something that you can do. The greater the divergence or the repeated measurements, the greater the random error. So you can see from this graph that the variability of the errors is quite diverse. So this is what we call a random error, something that you may not have control over. A measure with little random error is said to be a precise or a reliable measure. So for example, if you're measuring blood pressure, maybe having a more reliable way of measuring blood pressure would introduce little random error. So random error due to sampling or random error due to measurement is something that you need to anticipate, and oftentimes this is not avoidable. The second type of error, which is a systematic error, you can see that the error is clustered around some area. And this is the type of error that we can try to anticipate and control or minimize during a design stage of any epidemiologic study. There are three types of systematic errors that we look into: confounding, selection bias, and information bias. We'll discuss those in a greater detail in subsequent parts. So what is bias? So a bias, as I mentioned earlier, is a systematic error. So it's a systematic error, be it in the design, the conduct, or analysis of study that results in a mistaken estimate of an exposure's effect on risk or a disease. This is one definition. Another definition by Sackett says a bias is any process at any stage of inference which tends to produce results or conclusions that differ systematically from the truths. Both definitions have the same thing in common. They're both saying this is a systematic type of error. So we can anticipate a systematic type of error, and we can try to do something about a systematic error. We may not be able to control a random error. We can try to ensure we have reliable measures or ways of assessing our exposure of interest or our outcome of interest to minimize random error. But systematic error is something that we have to be careful about and take into account in our epidemiologic studies. So in subsequent slides, we'll discuss about the utility of causal diagrams or DAGs, directed acyclic graphs, and their utility in identifying sources of bias and in mitigating the impact of sources of bias. So let's start with some basic definitions. DAGs have two components. So we're going to use some terminologies. Don't be alarmed with the different terminologies that we'll use. We have interchangeable or alternative words that we use, try to make them a little bit easier. We're going to use A in our causal diagrams to mean a cause or an exposure. This is the same thing that we have seen in prior slides. It could be denoted as an E, but for our purpose, we're using A. It means the same thing. And then we'll use Y to indicate effect. So in in DAG language, we have two components. The first one is called a node or a factor or a variable. The second one is an edge or a unidirectional arrow that indicates the causal effect. So we have the node, this is a node, this is a node, and then we have the edge. So the variables are ordered based on time effects. So causation, time flows from the left to the right, indicating a cause. So the assumption we make take the form of lines or edges going from one node to the other. Let's try to break the word a little bit and understand the definition more. So we're saying it's directed. What it means is no bidirectional arrows. So we're talking about causal. In associations, we've seen the bidirectional arrows. But here, when we're talking about causal diagrams, we're talking about directed, no bidirectional arrows. The second one is we're saying they are acyclic, so there are no loops. The last one is they are temporally ordered, which means time flows from left to right. So those are some of the basic things that we need to understand about DAGs. Let's get back to the same example that we have seen earlier, to the ice cream example. So we have on the left side a dry, hot, and sunny weather. So we can depict that here. And we have ice cream and we have sunburn. So you can see that because we believe summer causes ice cream consumption increase, we have a causal diagram, or we have an arrow. By the same token, we have the same arrow from the summer weather to sunburn, but we don't have an arrow between ice cream consumption and sunburn. So there is no causal effect, no arrow between the two, or that is something that we are trying to test. And we'll see some more examples in subsequent slides. So let's look at the simple example where socioeconomic status affects educational attainment, which in turn affects income. But as you can see from our prior definition, we said it's acyclic, which means no loops. If we look at this, we have a loop, so we cannot have loops. This cannot be appropriate in a causal diagram, so we cannot have loops. If we add a little bit more specificity, we can say, well, let's take socioeconomic status in childhood affecting income, which in turn affecting adulthood socioeconomic status. This would be an appropriate description of a DAG. As you can see, in the process of drawing this DAG, you're also clarifying your research question. So by putting your DAG, you are enhancing the ability to ask your research question. You're adding specificity to the research question, in addition to fulfilling the criteria required by the DAG, which in this case is not having a loop. So let's look at additional terminologies. So a path is a sequence of adjacent edges. So we could have C, A, Y, or C leading to Y, or C affecting Y. So for example, we can say C, A, Y, that is one path, or we could have another path, which is A, C, Y. So this is another path. So it's a sequence of adjacent paths, one next to the other. There are some additional terminologies that I want to discuss in DAGs. Those might be intuitive, but they're important, as we'll include them in subsequent slides. The first one is a parent. A parent is, as the name implies, is nothing but a direct cause of a particular variable. So for example, a parent is a direct cause for a child. So we can take this. The second one is an ancestor. An ancestor can be a direct cause, for example, a parent, or an indirect cause of a particular variable. So for example, if we take the child, the direct cause is the parent, and the indirect cause can be a grandparent. So it could be, an ancestor could be a direct cause or an indirect cause of a particular variable. A child is the direct effect of a particular variable. So for example, child is a direct effect of a parent. This is the same as an exposure outcome described in a different way. And lastly, we use the word descendant, which means it's a direct effect of a child, or, for example, in this case, a child, or an indirect effect a grandchild of a particular variable. So the grandchild is a descendant of the grandparent. So those are, intuitive definitions, but something that we'll continue to use them. This is a very important concept in DAGs, and I really encourage everyone to spend some time going over this. It's an important concept in DAG, and oftentimes it comes in handy trying to understand some of the ways that we think about issues of confounders, which we'll discuss in the next part. So a variable is a collider on a path if the path enters and leaves the variable using an arrowhead. So it's a term suggested by the collision of causal forces at a variable. If you have two arrowheads meeting here, so you have U1 entering, U2 entering here, so the two are colliding. That's where the word collider comes from. So a major source in evaluating an effect of A, for example, the exposure in this case, on Y often arises when selection into the population under study or in the study sample is affected by something else, which is by both A and Y. Such selection is a source of bias even if they are independent of selection. So even if A and Y, the exposure and the outcome, are independent, if their selection is dependent by a common effect, this common effect is often called a collider. We get this issue of a collider bias. And a collider is specific to a path. So depending on which path you're looking at. For example, if we look at A, if we are talking about the path between U1, A, and U2, you can see that this is a collider because the two arrows are meeting here. But A is not a collider if you're focusing on a different path. For example, U1 going to A to T, because we don't have those two arrows meeting at A. So it's a path-dependent definition. Why is this important? It is important because a path can be blocked by a collider, which is a common effect, in other words. So for example, if we look at the paths A, Y, C, it is blocked by a collider because here we have this collider, Y. We have an arrow from A going here, from the C going here. Y is a collider, but it's dependent on which path we are focusing. If we look at another path, for example, A, C, Y, Y is not a collider because we don't have that common effect that the two arrows meeting on that path. So being a collider is really important to understand that if it is on a specific path. There is another terminology oftentimes we use in DAG. It is called conditioning. So conditioning is represented by a box around a variable. So if you see a box around a variable, it means conditioning. What do we mean by conditioning? So it either means in simple ways, this is something that we'll discuss in subsequent lectures, but it could mean simple stratification or adjustment or matching in order to examine the association between the exposure A and the outcome Y within the labels of a conditioned variable. But conditioning on a collider or on a descendant of a collider can unblock the path. So remember how a collider blocks a path. Conditioning on a collider can unblock a path. And this is an important concept, and we'll discuss those when we talk about bias, different type of bias, how this plays out. So conditioning, however, on a non-collider blocks the paths. This is different. If you condition on a collider, it unblocks the paths or it opens the paths. So earlier, if you remember, when we had the paths between A, Y, C, we say the paths was blocked by a collider. But if we condition on Y, it unblocks the paths. You can think of conditioning as adjusting or controlling, something that we'll discuss in confounding, just for simplistic purposes. So if we look at this path, C is a non-collider because we don't have the two arrows going into C. But if we look at the paths A, C, Y, and if we condition on C, which is a non-collider, conditioning on a non-collider blocks the path. So it blocks the path after you condition a path on a non-collider. If you have a path with no collider or condition on non-colliders, it is called an open path, which means you'll be able to evaluate or examine the relationship. So let's look at some simple examples using the following practice, trying to find an open path between A and Y. So a collider, trying to remember the definition, is a path-dependent concept. Let's look at this path. So if we look at the path between A, M, Y, where M is not a collider, if you remember, because we don't have the two arrows going into M. If we look at the path AMY, conditioning on a non-collider blocks a path. Therefore, the AMY path is blocked because we've conditioned it on a non-collider. Let's look at another example. If we go from A, C, L, D, Y, so the path is from here. Remember, always for a path to work, you have to go to the adjacent nodes. We would say that the path is blocked because we have a collider on the path. Remember, a path is blocked by a collider. What is our collider in this case? We have a D, which is a collider. The two arrows are meeting on D. However, if we look at this, a path between A, C, and Y, it's an open path. We don't have a collider, or we are not conditioning on a non-collider. Similarly, if we look at the path between A, C, U, Y, we also have an open path. I know this was a lot, but I would encourage you to go over this and learn the terminologies, because this is an important concept that would be quite useful in discussing study designs. And there are many benefits to DAG, including clarifying study questions, as I mentioned, adding specificity to your study questions. And it also represents our qualitative expert knowledge and whatever prior assumptions that we have about relationships of variables or a causal structure of variables. Secondly, it helps to classify bias, the different types of bias that we have. It is also an important tool to identify potential problems that we may have in a study design and analysis. If we take this example as concluding our session on DAG, looking at the two news articles, the first one is talking about causation. So can caffeine treat depression? let's say for the source of caffeine, in this case is coffee. So in the first one, we have coffee consumption affecting or causing sleep problems, and sleep problems causing depression. So that is a causation. But in the second one, if we look at if there is a link between caffeine and depression, we might say that both depression and maybe gastrointestinal symptoms are associated by an underlying psychosocial stress, which in part affects caffeine consumption. And there's really no causal association between depression and caffeine consumption or coffee consumption. And as you can see, both are trying to answer similar questions, but approaching it differently. And the use of DAGs sometimes helps to clarify those causal questions. So in conclusion, we have seen what a bias is, what a valid study is, and how we can use DAG as a way to address some of the relationship that we have between an exposure and an outcome. And in subsequent parts, we'll talk about confounding, how we can use the utilities of DAG to address confounding. We'll talk about selection bias and information bias.